Where is this message?
You can't see the menu, right?
Yeah. I think might be.
That's because it's the laser winding.
Oh, do I need to tab you?
Okay, I got it.
Okay. Good morning, everybody. So let's get started. We are very happy for one of our alumnus coming back here. Many of you in this room and also outside know Ammar. He graduated 2020, I think, just when the COVID had just started. I think you were almost the first.
Lockdown remote graduates.
Yes. So remote graduate, and things have just moved very quickly over the last 3 years. Ammar is a senior researcher at Microsoft currently, working on the DeepSpeed library with Yuxiong He and then the DeepSpeed team. He is the lead developer of the DeepSpeed Mixture of Experts, or MOE, what we call it, systems that supports both training and inference of the MOE models at scale. He received his BS and MS and PhD degree in computer science from the National University of Science and Technology, Pakistan, Yuxiong He University in the South Korea, and finally the PhD from OSU. His current research focus lies on the intersection of the high-performance systems and large-scale training and inference of DL models. He previously worked on a Java-based message passing interface and nested parallelism with OpenMP and MPI for scientific applications. He has published several papers in conferences and journals related to these research areas. He actively contributed to the various projects in my group when he was there on the MRPs2 project, and especially the GPU side, the MRPs2 GDR, high performance MPI for GPU clusters, OMV, and he actually started the IDL project actually. When we were discussing, I think when the field was just coming up, nobody knew how to do distributed training. I think we had the first paper, OSU Cafe, we call it. At that time, Cafe was running only on a single node. And then Ammar actually extended that to distributed model, and that was a PPOP paper. And I remember there was a lot of excitement there just to say that, oh, now things can scale distributed things. And with that project, actually, we started the HiDL, which is high performance DL, which have been going to high performance deep learning, machine learning. And also as a part of that, we started this course at OSU. I think many of you have taken the HiDL course. It was one of the first version. We worked with Hari, Ammar and me, started putting it as a class because we were giving a lot of tutorials on these new directions. And then we decided, why don't we convert it into a regular class? And then it has actually for last 5 years, 6 years, we've been offering that class, and it has become a regular course also. I think many of you have been taking, and also a lot of tutorials. I think Ammar has in that part.
12, I think.
Yeah, so he contributed to almost 12 tutorials we gave. The IDL was very hot topic, and that tutorial is still continuing, by the way. I think other people have picked up here, Quentin, Nauras, and all the new students. So we are still continuing and offering. Just in a few weeks, next month, we'll offer it at IDL, Hot Eye conference. I believe that's how we started. That's how we started. So a lot of excitement things are going on. At that time, I think, I don't remember in the OSU Cafe, I don't know through how many GPUs we scaled.
160.
160. Today he will put few more zeros there. Okay. So with that background, I think let's give a very hearty welcome to Ammar. And And his talk will be trillion parameter scale model training and inference with DeepSpeed. So please.
Thank you, Dr. Panda. That was a fairly long introduction. And a fun fact, the first paper, the PPOP paper, Yuxiong was a shepherd.
Yes.
So it's a small world, you know. Okay, well, great to see you all. My name's Ammar Ahmad Awan, for those of you who don't know. I have been working with the DeepSpeed team ever since I joined with Microsoft back in June of 2020. As Dr. Panda said, we were all remote at the time, so everything was remote. Graduation was remote, joining the company was remote. But I have loved working with the DeepSpeed team. And I'm going to give us sort of like an overview talk in the first section. So we cover these, you know, few aspects of what we do in DeepSpeed, what kind of researchers. It's a team of researchers, primarily. Pretty much everyone on the team has a PhD in their own sub area. And so we just work together. And DeepSpeed is our research vehicle so that we, you know, just like Mbappage, there's a lot of similarities in the project in some sense. Like a lot of you work on the Mbappage project here, and then you use that as a vehicle to publish your research and show that the system actually works. Similar to that, in the DeepSpeed team, we also have a GitHub, and it's an open source project. That's why I'm, you know, fairly open to talk about anything or any of the research aspects as well. There's nothing hidden, confidential here. We are a group of researchers who work together on different areas and collectively combine all our energies and use DeepSpeed as a vehicle for moving this field forward. So I think with that, these slides are fairly outdated now because everything in AI is pretty much like in a 2-day update cycle. So, but anyways, just for the sake of completeness, why large models are important, I think by now everyone in this room and pretty much everywhere in the world knows about large language models and why they're super important. But it's not that old, honestly. If you look at that 0.1M model back in 2018, it's a 94 million parameter model called ELMO, and then BERT, which a lot more of you know. BERT model was just 340 million parameters, and from there you can see the insane scale. And the largest dense model that I know of is the Megatron Turing TNLG model, trained with Microsoft and NVIDIA's collaboration. It used DeepSpeed and Megatron. And Turing is the modeling team at Microsoft, which made that happen. And so why do we care about them? Because the larger the model, the better the accuracy. So far, it has been a simple equation. You make the model bigger, you get better quality outputs. Interestingly, the model size is still growing, so we've still not, you know, reached a point where we say, okay, if we make it bigger, it doesn't become better. It still does. But the problem is we're kind of hitting a wall in terms of the hardware itself. It's also, we don't think that it has reached the accuracy limit yet. And another aspect which easily gets missed is that it's more compute efficient to train larger models than training several smaller models and then combining them. That's because the capability that comes with a very large model is just unmatched. So you cannot just combine smaller models to make a bigger model, which will act better. Caveat to that, maybe MOE is a different story, but regularly, no. So larger models are more efficient. So with that background, let's just, you know, look at this giant table. A lot of the people, when we first started Café here at OSU and like OSU Café effort and IDEO, we only used to work in the data parallel regime. So data parallelism is the simplest possible distributed training strategy that you can do. You have a model, you replicate it across as many GPUs as you have, and then you do communication. So the challenge there is the maximum number of parameters that you can support here. I'm writing like 1.2 billion, assuming a 40 gigabyte 800 GPU. So your limit to your model scale is your GPU memory. So if your GPU memory is 40 gigs, that's it. You cannot do anything better. But there are really good parts of data parallelism. It's very simple to do. You can scale to thousands of GPUs, has pretty good compute efficiency if you can increase the batch size. And there is absolutely no model rewrite needed. Just replicate everything and train. So use an all reduce or a reduce broadcast loop, and you're pretty much done. Saying that now is very easy. When we first started it, it wasn't. Even a single node to outside node scaling was hard. MPI had a lot of issues. We had large message collectives, never like explored in the context of MPI because never needed. You know, it's a workload determined, you know, sort of like what kind of designs would you do for collectives. So we were indeed the first ones, and And I say this because I know when I interviewed at Microsoft, people were like, oh, you are the guy. Okay, you're the one who started that. Okay, we know you. So I didn't have to explain a lot during my talk. And then, so data parallelism, the simplest. The next one is model parallelism. Model parallelism is an umbrella term. It can be used in multiple ways. But when we say model parallelism here, it's a specific form of model parallelism that we call tensor slicing or tensor parallelism. Basically, the way Megatron paper introduced it for transformer models. So it's only a part of the model called MLP, which gets distributed in a specific way called tensor parallelism. What it allows you to do is from that 1.2 billion parameter scale, you can now actually train a 20 billion model because NVIDIA has these DGX boxes. So you can go like 8 GPUs and then you say, okay, let's split the model on 8 GPUs. So now you can support almost like a 20 or 16 GPUs for the V100s. So you could, and why I say that is because it only works really good within the node. It's very hard to scale tensor parallelism across nodes because of the massive all reduce that is needed for realizing this time. So max parallelism approximately 16, with 800 is 8. You can't do any better. Compute efficiency is good, but it needs a model rewrite. You need to rewrite the model in a specific way. Well, people thought, okay, great, DP is great for max parallelism, so let's combine them. So NP plus DP is best of both worlds, still needs a model rewrite. And then we hit another limit and we said, okay, 20 billion is great, but it's not the best. Can we do higher? So we said, let's do pipeline parallelism. So pipeline parallelism is also sometimes called layer parallelism. So if you have 4 layers, you have 4 GPUs, put 1 layer on each GPU, make them extended. I'm just trying to make it really simple because actually working with pipeline parallelism is a big pain. And so it can go to 100 billion parameters, but the problem is it also has a limit. So pipeline stages, you can only do so much. So with 128, we saw that there are diminishing returns. You would not want to increase it any further. It needs a significant model rewrite, super hard to implement. And then you can combine PP with DP, and you can also combine all 3 of them, and then you can get great. But this is the problem. Nobody wants to do this. It's extremely hard to do it and get it right. And then training is a stochastic process anyway, so learning rate of 9.5 E minus 6 and E minus 5 can just destroy your whole intuition around training curves. This is going to just cause havoc. So what to do then? So very smart people at the DeepSpeed team thought of a great idea that they called Zero. It's called Zero Redundancy Optimizer. And it's basically a memory efficient way of realizing data parallelism. So Zero is still data parallelism, but it allows you to do all 3 in a way that is really good. So you have no model rewrite, which is great. You have excellent compute efficiency, similar to what you have in data parallelism. And then you have amazing scale at model, which was the blocker. So now you can train trillion parameter models on thousands of GPUs, and without doing any code rewriting, any model restructuring, any specific model-specific optimizations per se. So that's what we call Zero. And I'm going to give a sort of a deep dive into this topic, but I'm just giving an overview here. So this is a broad statement. Democratization of large model training requires easy-to-use solutions, and easy-to-use solutions that can also support large models with parallelism degrees that are in thousands, and also want to remain highly efficient. So this is a broad challenge that the DeepSpeed team sort of tackles through the Zero family of optimization that we're still continuing on because the hardware architecture is evolving and then model types are evolving sometimes. So this is purely in the context of transformer-based models, but what about other models too? And I know that everything pretty much is now a transformer, but there are other interesting aspects that we try to capture as well. So that's the broadest possible overview of parallelism. So it's like a primer for the whole talk. Now, just some of the achievements that the DeepSpeed team has been able to do. So we're literally reshaping the landscape for training. If you can see, this chart is really interesting. So you can see that the transformer size has become 240x over 2 years. So you can see it started from here, it's going at here, and people are saying we want to train a trillion or a 10 trillion model. And the GPU memory, though, is pretty flat. You see, it was 16 GB back when I was here at OSU, 32 GB V100s, and still today you get 800 or 800 with 80 GB. There's just a memory limit that you can't keep making these expensive memories bigger, right? So if you don't do anything with software, you will be bounded by this. And so DeepSpeed team's sort of contributions come in this area where you have these 0, 1, 0, 2, and 0, 3. So 0 family of optimizations has 3 stages. 0, 1 allows you to do a little bit better with removing some redundancy. Then 0, 2, even more. And then 0, 3 and 0, infinity is where you do offload, CPU offload, NVMe offload, as well as partitioning the entire model, even to the parameter level across all the GPUs that you have. And so that allows you to go, and that's why we call it 0, infinity, because it kind of provides you like infinite model scale. If you were to have that many GPUs, like you can train any scale of model with that. But it's a system capability. So we always emphasize that it's system capability. It doesn't mean that you can buy DeepSpeed and tomorrow you have a trillion parameter model. No, you're still going to do the hard work of actually training a trillion parameter model. And how we do that is with all these technologies. So there's 0, 0, infinity, 3D parallelism, which means combining these. Then memory and compute efficient MOE training. We have several optimized CUDA and ROCm, GPU specific kernels, gradient compression, sparse attention. So a bunch of really research oriented as well as like, production grade, technologies inside DeepSpeed that allow us to do this. So a question.
Sorry,
It's okay.
Here's here basically, you might see designating those solutions as good within one box, whether one box is 1 or 4 or 8 or 16 GPUs. Where do you place like systems like, for instance, the PTX GH200, where it's basically a super chip. The main selling point is 144 terabytes of basically memory. Is this now one box in your view? Or in essence, because of the emergence of those highly converged single box, as I really like to call it. Would you see that those techniques are not becoming as relevant? But I guess how do you position this work with respect?
So Grace Hopper, that's an interesting new thing. We've been hearing about it a lot in terms of design and theory, and all of that sounds really great. We have not yet experimented with an actual hardware piece. Before Grace Hopper, actually, there is a hopper that was supposed to come with something called a NV switch that scales across nodes. And so like a 256 GPU switch. We've not yet experimented with that either. So we don't know, but I think these technologies are fairly, like at least the 0 infinity technology is fairly independent. So we're hoping it will actually get a boost. Getting 0 infinity to scale and actually train models with high speed is still challenging because it does, it's just fitting too many parameters on a, so like each step is probably taking 30 seconds or something. So it will improve if you could, somehow say, oh, let's just consider 256 GPUs as one box and now scale them to tens of them. So I think there is value. It's just that the hardware is not there yet. So yeah, but when it comes, it will be really the first one to use it. Any follow-ups? Yeah, so that was a great question. That's really the cutting edge of hardware that we are hoping to experiment with soon. So moving from scale to speed, scale is when we're talking about model scale as well as GPU scale, but raw speed it matters. Like with what throughput, with how many samples per second you're moving. So DeepSpeed team a long time ago in some old, really old days of V100 GPUs actually broke the fastest BERT training record. And that was through DeepSpeed and 0. And you can see like from 236 minutes, it came down to 44 minutes on using 1024 V100 GPUs. That record, was really the thing that started the movement of DeepSpeed within Microsoft as well as then the outside adoption. Then here we are trying to talk about, scale. So like speed with scale is also important. So what if you had really good speed on the single GPU because you use optimized kernels, but then if it doesn't scale or slows down the scaling part, what will happen? So here we are just doing a sort of like a benchmark trillion parameter model and seeing what will be the perfect linear scale. And then you'll be like, okay, this is the wrong line. How can you be more than the linear scale? So it turns out that there's a really interesting superlinear speedup phenomena because we are able to increase the batch size with 0, because now you've distributed your model states such that you're now across all GPUs. And so you remove the redundancy. So let's say in the old world, you were only able to train with a batch size of 2 per GPU, but now you can train with 4 per GPU. So you have a larger batch size, and which means higher throughput per GPU. And so that's how we get this superlinear speedup. The first time I saw a chart, because coming from HPC background, you're like always trying to get near linear is still super hard. How do you do that? But it's possible here because of the large batch size.
There is one question from Zoom.
Oh, okay.
Then you can unmute yourself and ask the question.
Yeah. We can hear you, but maybe speak a bit louder. Or if someone can read out the question from there.
No, just raise hand.
Oh, raised hand. Okay.
Or post it in the chat. You can see the chat.
I can see the chat. Yeah, but I can't go there. I think it was
I can read it.
Sure.
No, like he can see the chat here.
Yeah.
Okay.
Sure. We'll take on as it comes. So then because we work at Microsoft and democratization is sort of a mission and within the company itself, like how can we make it available for all? So this is the line. So zero infinity basically is a line which we started with this notion of what if you only have a single GPU box and you're not training in the cloud, or you don't have a lot of them, or you are limited by your budget. So here, this line zero infinity with NVMe is showing now, well, if you have one DGX box with 16 GPUs, you can actually experiment with a trillion parameter model. And this is kind of like saying you're now able to train almost a 700x larger model compared to standard data parallelism. So that's a big achievement. Now, nobody is saying that you're going to actually train a trillion parameter model on a single, because it's going to take ages. But from a model science perspective, you're no longer limited in the thought process that you have. So you can say, oh, I want to try like a 20 billion model with this new model design or architecture. I have this positional embedding that I want to experiment with. Then that allows you to do even on a single GPU box. Yeah.
Are all of these models same hardware?
Same hardware. Yeah. Same one DGX box with 16 GPUs.
Oh.
V100s. Yeah.
Why does this speed up or anything?
This is not a speed up. This is the number of parameters of a model that you can. It's not the speed, it's the scale of the model, size of the model. Yeah, that would be awesome, but that's impossible. Okay, so then moving on to another direction, this is the first thing when I joined Microsoft, I worked on this with an intern. And the idea is that there are still a lot of older Azure instances which does not have the awesome IB interconnects. So what do you do about those? You still have GPUs on them, but you don't have good interconnects. So we explored this scheme called one-bit compression schemes, and Atom is the name of the optimizer. So we explored in one-bit Atom. It essentially reduces the communication by 5x. It doesn't speed up by 5x because you have to still do some warm-up phase and then the optimized phase. But 3.5x faster training. So it kind of allowed us to scale on older instances. So things which were unfeasible, I actually do have some more detailed slides on this one. It was almost, like we were infeasible to train on multiple GPUs because of this phenomena here. So like for those of you who are on Zoom, you can see like the gray line here is saying, well, there's absolutely no use to use more nodes because I'm going to get terrible performance. But if you use this compression scheme, you're actually able to scale pretty much. So higher is better here. This is the samples per second. You can see the other nice phenomena here is that one-bit Atom on Ethernet is kind of similar to a baseline Atom on InfiniBand. So we were able, through software compression, we were able to bring it to a point where it becomes useful to do multiple GPUs. Before I go next, I'll just take this question. So Vardhan is asking, for the optimized CUDA kernel, is it GPU dependent? Does Zero automatically support custom kernels for arbitrary models and GPU hardware? So optimized CUDA kernels are for NVIDIA GPUs, but because of ROCm, they're automatically applicable to an AMD GPUs. We've not yet experimented with Intel, but they're also trying to do some kind of transparent conversion. Zero automatically supports pretty much everything that you have on the kernel level because Zero is only for distribution, not for your one GPU thing. So it will take advantage of pretty much any model. Caveat that we only have optimized kernels for transformers, but if you have optimized kernels for anything else, it should still take advantage of it. Right, moving to, this is a bit more research-oriented line of work we did. This, I think, was published at NeurIPS. Someone who used to work at Microsoft, they have left now. They used to work on sparse attention, so you can support 10x longer sequences and also up to 6x faster scheme. These are all along the compressed training line. So this is a fairly interesting idea. You basically progressively drop layers based on their value in the end accuracy that you achieve. And that's how you can make the model smaller. Changing from training to the inference side a little bit. Inference is relatively new for DeepSpeed. At least for the last 2 years, we've been doing that. And then the reason is because now we have sort of reached the point where we're like, okay, these models are useful things. How do you use them? How do you deploy them? And so here I'm giving you this. This was presented. So there is a whole 1-hour talk on this SC last year that I also happened to present. But giving you the scenario from all sort of like BERT-based style models from 100 million coming all the way to like trillions of parameters. And as you can see, there are like these 3 families, right? So you have dense single GPU models that you can deploy on a single GPU. Then you have dense multi-GPU cases where there are models which are big enough that even with all the compression in the world, you can just not fit on a single node. And you have to do single GPU. And then finally, there is this sparse MOE models that you can potentially deploy on hundreds of GPUs. That's just because of the characteristics of the model themselves. And so here we are trying to show like there is a family of optimizations needed. One solution would not fit all. And so DeepSpeed has this broad set of optimizations for each of these model families, and they're all coherently connected. They provide pretty like same API for all of these model improvements. So you just wrap your model in DeepSpeed, and then it becomes faster by these many, 12x, 7x, 5x, depending on the model scale.
So when you mean compressed training, you're just dropping certain layers based on its impact on the final accuracy.
Right.
You are not, let's say, using any sort of regular zip compression.
No. So this is very model specific, not model. Those would be model agnostic optimization, like a system side optimizations. Yeah. They're also very interesting. I think someone wanted to explore, but they were an intern and they might have done it independently, but not like officially.
Okay.
Yeah, that's an interesting line. So if you have any ideas, we can brainstorm a bit on that. So then usability. So I think in this space, the simplest gets the most points usually, because everyone wants to use AI. If you have a pip install package, it's going to get adoption pretty fast. If you don't have it, then people are like, oh, this is too hard to build. So we worked a lot actually in our software team to make things really simple for people to run, even on like your normal laptops. And so DeepSpeed kind of works on MacBooks now, but just for experimentation. The other part is like, yes, people want to do it scalable too. And so here we're trying to show like with the PyTorch distributed data parallel or DDP, your limit was 1.4 billion. Now you can train a trillion parameter, same API, no change, no code change needed. So that's kind of like the usability power. Then I hope people know about Hugging Face. If you don't, just make sure you learn about Hugging Face. Like that's the model world for pretty much everyone. Like the latest model gets released overnight there. Like you train a model today, Llama 2 from Meta, and you like make billion-dollar deals, and then tomorrow that's on Hugging Face, freely available. You can download, use it. So make sure you learn Hugging Face a little bit. But as a student, so I'm comparing like student audience, not telling the professors to learn about it. And then Hugging Face works really closely with DeepSpeed. So they've integrated in a way that if you use Hugging Face's trainer, you can run in a DeepSpeed mode. So now you can transparently fine-tune, models at scale, taking all the good technology under the hood from DeepSpeed. PyTorch Lightning is yet another package like that. So it's a different kind of trainer. It's also integrated with DeepSpeed. All the optimizations are fairly infrastructure agnostic. You can run it on Azure ML or Azure VMs or local nodes or your own GPU clusters or Slurm. And people have been extending. So we always take PRs to support different launchers and environments. So with that, just giving a small code snippet. I promise we don't have too many codes in my slides. Here's you have like a Torch model. All you need to do is wrap with the DeepSpeed engine with this API, and then you continue with your training loop. The magic configurations happen here. So we call it a dsconfig. It's a JSON or a Python dictionary if you are more comfortable with that. You define your optimizer, use 0 family of optimizations, and then you're pretty much done. So you can train, like we did this exercise with the student workshop where we started with a 100 million model, and the stage was 0. And then we progressively increase the model size and we say, let's go stage 1, 2, 3, and you see where it will run out of memory. You set the next stage, it will then start training. it's pretty cool. So do give it a try and let me know if you run into issues. This slide again is fairly old, but we have a 10x year-over-year growth for DeepSpeed usage, 6 million plus installs, several hundred unique contributors now, and 1.6K public packages are now having hard dependencies on DeepSpeed. So basically, the dependency package line through Python is determined through that. And so a lot of other companies are also using us. Our competitors are sometimes actually supporting DeepSpeed and giving us PR. So it's a fairly interesting project in that sense. It's open source, so everyone's happy about that. Some of the national labs are also using the Oak Ridge folks, Livermore folks. The L-band team actually also happens to use DeepSpeed quite a bit. So that's fairly interesting. And finally, this is the last sort of overview slide, DeepSpeed chat. We did this work 2 months ago. This is one of the biggest, AI things that people know about it. So AI used to be like a AI only folks thing, and then ChatGPT happened, and sort of the iPhone moment of AI happened in some sense, and everyone wanted to now we want to train a chat style model. Well, chat style models are trained slightly differently. So it's trained with something called RLHF. And so we had to sort of make DeepSpeed adapt to it. And so now DeepSpeed supports chat style training. And these are some of the results. So compared to state of the art, we are able to again support much larger models, much higher throughput. This is very, very recent and super interesting. It has a lot of bugs too. So if you create GitHub issues and PRs, we welcome them. It also kicked us off in a frenzy. We were like a top 10 trending GitHub projects after this release for several weeks. And then that's our also first international release. So we went into the Chinese and Japanese market and we came on pretty much all the leaderboards there on their Twitter kind of spaces. And so that's like the cool aspects of DeepSpeed. So now I will go into the deep dive of Zero Infinity. But before that, if there are any higher level questions.
Yes, so I have 2 questions. First one is use the term democratization. This is also at the heart of ICICLE. I'm wondering, in the context of DeepSpeed, what does this stand for?
Sure. So when we say democratization, we basically mean that let's say there is a PhD student and they want to, and they're a model, DL model science student, and they're trying to experiment with the model. And they are limited by the kind of GPUs they can access, or the kind of GPUs that their NSF project would give them a grant for, or like a cluster access, right? And they are trying to access something on Azure. They most likely are going to just get one VM, install something on it, try it out, and then be done. They don't have the capability to say, oh, I'm going to get thousands of GPUs on Azure or thousands of GPUs of a cluster and then train my model. Because model training is not like your coding, where for example, when I used to run these all reduced benchmarks on 20,000 GPU scale, right? But that's short running. So you want to just see if your collective algorithm is doing good, right? You can run on 2,000 GPUs, do it for 20 minutes, come out. With training, you just keep running, for days or weeks, you have to keep occupying those GPUs. So they're charged by the hour, or SUs in terms of your HPC resources, right? Which you don't have. So when it comes to DeepSpeed, we're trying to work on different technologies, research different technologies or approaches, which allows people who do not have a lot of GPUs or do not have a big budget can still try to experiment with larger models. Because my first slide was why large models? Because they're important and because they're good quality and because that they're going to kick off the next generation of AI. And so to support that, we do our best. Obviously, in someone's world, 16 GPUs, DGX blocks is not democratization. But compared to thousands of GPUs, it is still democratization, that you can just buy one box for the department and everyone is now trying to train their experiment with their large model on a single box instead of getting cluster access and setting up SSH connections and whatnot. So that's it's a loose term in some sense, but yeah. Does that give you?
So the second question is, so I think small language model is already very expensive. So the last thing you want is to train it with wrong set of microparameters. So I'm wondering, does DeepSpeed, how would DeepSpeed approach hybrid path optimization? Is there any rules that we provide, or is that something fairly hard to read?
Yeah, that's a great question. In DeepSpeed, we do not do hyperparameter optimizations. The teams at Microsoft, they are specialists, so we let them do their hyperparameter tuning themselves. The outsiders that I know of, they use like various frameworks to get there. Sometimes it's just a model scientist's intuition. Like I would just never understand why it's 9.6 E minus 5, right? Like no idea, but they will know, right? Because they know that they're training the model. So think of DeepSpeed as a systems team supporting model teams to train their models. So we work closely with them. For first party, that's possible. For third party is usually through GitHub issues and PRs, and they're like, oh, this paper published this learning rate, but when we tried with DeepSpeed, it's breaking. And then we're like, oh yeah, because we have the scheduler or loss scale, and we'll change that. So there are certain system parameters that deal with, they coincide with the sort of model parameters or hyperparameters. So we do take care of them, but not like, there is no auto learner kind of thing here in DeepSpeed, which will let you know, oh, this is the best learning rate for the model. At least not yet, maybe in future. So, yeah.
So, just a quick question. I know that you guys use ICICLE towards communication. From a systems perspective, what are the other optimizations that DeepSpeed is using at a high level to get this kind of story?
Did you mention SICLE project, SCCL or
SCCL?
SCCL, yeah. So Nickel, yeah. So SICLE is an interesting research project. It's built on top of Nickel. It just tries to improve Nickel. In DeepSpeed, we support both, but mostly for these experiments or results, we've been relying on black box Nickel. We didn't do a lot of things because we come from a more application perspective. So like instead of, let's say, writing a new collective, we will change the application to use the collectives more efficiently. Like we'll partition it in a way that we will like, oh, we can do an all-gather here instead of doing an all-reduce. So that's why we have not yet, like there were certain parts of it, like for MOE specific, where we went down, or like for 1-bit Atom, Nickel didn't have specific things. So we had to go down a stack, and that's where Quentin's work came in when we said, okay, let's write our own COM backend. So if there is nothing in Nickel or PyTorch is not exposing it, we can call the C++ library directly. PyTorch is really cool about it. TensorFlow was so not. So it's much simpler to hack ops into PyTorch, written in C++, and you can call them from Python. So that's what we did. Several questions. So you first.
So I want to ask a follow-up question on the parameter. So we have any island with that one for the answer. For example, I was good at that also like learning all, but like actually don't find out like how to set up those kind of you already use it before, but I don't know whether it's quality.
For DeepSpeed configurations, we have this project called auto tuning. So we do have that kind of tuning support. So it will run on like a few hundred experiments and tell you the right, like which 0 state should you use, or which family should be turned on, if you should turn on offload or not. That thing exists, but we won't give you like which is the best learning rate for you. That's the job of a hyperparameter optimization suite like Optuna or whatever these, Python. There are several Python libraries that allow you to do just that. Like if you have a model, let's say 100 million parameters, you run it 50 times and determine which one goes down the fastest, then that's your good learning rate. Choose that learning rate, then you plug it into DeepSpeed. But like in terms of 0 state selection or offload on or NVMe, or should we use it or not, those kind of things can be determined auto tuning. Again, intuition wins over tuning because tuning takes time and GPU resources. But we do have a whole software suite. It basically takes Hugging Face models and creates a table for you. And so now we've done it once. If you are in that family of model size and scale and type, you can pick from there. Like you don't have to tune it. But if you slightly change it, then you can rerun the tuner and it will spit out the right sort of DeepSpeed flags for you. So yeah.
There actually exists a table. Like
there does exist a table for, at least for Hugging Face models, which are reasonable size, not trillion parameter. There's no one who knows hyperparameters for trillion parameters, but like 100 million to, let's say, 5 billion parameter model scale. There is a table on, like if you search for DeepSpeed auto tuning, there is a page, there is a README that will show you that. Okay, so.
When you get about this story, you came across, Hugging Face and PyTorch Lightning and something still way to bring this technology to the masses. From at least the ICT standpoint, we see applications that are nowhere near that. In essence, they're not even yet at the PyTorch level, let alone moving from a PyTorch model to the PyTorch Lightning. This is another step.
Right.
So I was curious. Do you have any thoughts on that part of the organization? Because potentially could be a valuable opportunity for Microsoft as well to argue that now we can bring this into any Python runtime, and now instead of making A100s or let alone DTX boxes, now you can do E4s, which are they're cheap.
Yeah.
So any thoughts on how the number things among the use cases, and keeping in mind that many users are still not even on the PyTorch, because calling into PyTorch without even knowing.
Yeah.
You can't expand this much bigger process.
That's a really good question. It's probably something we also struggle with a bit. So DeepSpeed is primarily built on top of PyTorch. So like our fundamental sort of limitation is everything and anything that works with PyTorch, we make it sort of workable with it. But then there's also things like AMD team, for example, did not have PyTorch support. They approached us. We said, well, it will be a good idea to support PyTorch first, and then we can work with you. So that's how they did it. So they created a PR to DeepSpeed, but they also created a PR to PyTorch, and then we tested them together on AMD GPUs. So that's how it went by. Good thing is the Python ecosystem is fairly simple. Like PyTorch code is like Python code. A lot of people, it's much simpler than like compile C++. And so people are able to contribute patches to PyTorch higher level and say, oh, there is this op we support now. Can DeepSpeed support it? And we're like, okay, sure. If it's in PyTorch, we'll just change the dependency version, say PyTorch 1.x onward or 2.x onward, we can do this. Outside of PyTorch, the only thing we have supported is Nickel MPI. They are agnostic. But like then I don't know, why would you use DeepSpeed if you don't have a PyTorch model? If you have a TensorFlow model, might not make a lot of sense to use DeepSpeed. So does that give some maybe Kuyas, you had first? Yeah.
Earlier you mentioned about large language models going to get much bandwidth, right? And it costs a lot to train. So would DeepSpeed be beneficial for fine-tuning these like large language models for specialized domains, or is it only for the training?
No, it's a lot. So Hugging Face is all fine-tuning, right? So Hugging Face is pre-trained models available. You download them and then you do your own task fine-tuning. So DeepSpeed supports that 100%, out of the box. Pre-training and fine-tuning, we don't make a distinction. It will support pretty much everything when it comes to fine-tuning. Unfortunately, there is no 530 billion model that you can fine-tune today, but like a 175 billion GPT style model available like Bloom, we fine-tune it all the time with DeepSpeed. Yeah.
A follow-up question, let's say I want to reach in class. It's a big package because I don't have the hardware and the SU to go to
right.
Like
that's a model client thing. So you could just say, if accuracy, blah, 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 reach threshold, just quit the training. Like DeepSpeed doesn't have to do anything for you. Like model science is pretty agnostic to what DeepSpeed does. You can define your own early stopping criteria, or this loss curve, or this perplexity value, or whatever, and then you just stop the training. DeepSpeed does not control your training pipeline. It extends your training pipeline.
I want to ask about your experiences in sort of supporting DeepSpeed and some of the different use cases you're seeing. Right? So DeepSpeed has a really wide options. Clearly, I'm trying to train the biggest large language model possible. And I've got to look at a certain intersection. But the rest of the world is looking at other sizes and whatnot. I'm wondering if DeepSpeed has transformed the takes on the clusters that you're seeing. For instance, is anyone using CPU in like this?
Yeah, there is a huge variety. So when this thing came out, Stable Diffusion, right, this image generation model, that was the first time we said, well, DeepSpeed should work on a single GPU. Before that, we never even cared about a single GPU. So we actually reverse engineered DeepSpeed a little bit to check, like, for if world size is 1, what do you do? So Stable Diffusion kind of works on your MacBooks and on your this has an NVIDIA GPU. So we kind of made it supported there. So it works from a single GPU, like a 20 million parameter model, all the way to like a trillion model with thousands of GPUs. And it's very challenging. Like if you go on our GitHub and you'll see like there are 700 open issues. We're a team of like 20 people max. And only like 5 people are the only people who know all the issues. The other we need to train them and learn how to actually resolve them. So a lot of community is helping us resolve these issues because they're such diverse code bases. It's hard to support open source in general. I think all PyTorch, like all open source projects have this issue. Like PyTorch has, I don't know, thousands of open issues. They don't know just how, when and where, but people, get to it and resolve it if they need to. That's how DeepSpeed is also sort of designed. Like there is a best effort open source things, and if there is a business critical thing, then it's like whole team just works on that. So that it's like a very dynamic state. But we do work really closely with users. So we are responsive on Git. At least I lead this weekly sync where we go over these GitHub issues and we say, okay, let's triage them. This is a training issue. This is a chat issue. This is an inference issue. Who in the team knows? Let's assign them, trying to achieve, some kind of like responsiveness to the users. Was that your? Yeah. Perfect. Okay. All right.
Currently, we only work with NVIDIA GPUs or
NVIDIA, AMD, and the Habana and the Intel upcoming architecture. They're using it. We don't have hardware access, but those who have, they've said that it works. Okay. AMD, we have access. So AMD, we have official support. The MI200s or MI100 also, 200 also.
Do you guys think of FPGAs at all, or is not?
So FPGAs are interesting, but we used to have a whole FPGA team within Microsoft who used to work on FPGAs, but things with GPUs have just gone really, really advanced. So it hasn't, like for inference, maybe still FPGAs would be there, but for training, I'm not aware of at least people using FPGA for training. Yeah. It's mostly GPUs, NVIDIA GPUs, and then, or if you talk about Google as TPUs, but others are AMD GPUs are coming as well. Yeah, quite a bit. Yeah. Okay, so this is a quick deep dive into zero infinity. I don't know how I'm doing on time. We have 15 minutes. Okay, so we'll probably do one deep dive, or we'll see how it goes. So I think by now I've talked about this chart quite a bit, so I'm hoping I can go over quickly. There are three main things: the GPU memory wall, the accessibility to large model training, and then the model code refactoring. And these are sort of like, you can think of them as pain points, right? So let's talk about the first one. So GPU memory wall, it's pretty clear that there is no way we're going to get like a terabyte GPU, right? It's 80 gigs, maybe it will be go to 100 gigs. How do we support the model growth? So that was the fundamental question for the Zero team or DeepSpeed team, right? Then accessibility to large model training. So right when we started, you needed like GPT-3 is 175 billion. You needed about 256 GPUs to fine tune it. Who has the budget to do it? Like, how would you do it? Even if you have a small data set, you still need these GPUs. So very limited access for most teams in the world. 256 GPUs is a lot. Even within Microsoft, I don't get the liberty or luxury to use 256 GPUs at will. It's more like we do coordination and a little bit of fighting and some convincing. So so GPUs are expensive, scarce resource. And then model code refactoring, this is the one most people hate anyways, because as soon as you change a little bit of software, then you're like, oh, my model is not training, the previous version is training. A lot of people within Microsoft I know are training with old fixed versions of PyTorch, DeepSpeed, something like, I'm a model scientist, I don't care about your latest API. All I care about is my model's quality. So your previous version gave me better quality. And so nobody wants model code refactoring. And so that's the three sort of main challenges that the team is dealing with. And so how do we go beyond GPU memory? We've talked a bit about it. Just this is a bit more deeper dive, right? So GPU memory, if you can see, is like 0.1. It's really a 0.5. It's a really small percentage of your overall memory available in a GTX2 node. So the blue is GPU, the orange is CPU, and then the green is the NVMe storage. There's lots of it, right? And it's also pretty fast. So can you leverage it, right? So if you leverage that, you can actually do a 32 trillion model on 32 nodes, or a single trillion, like 1 trillion on a single node, right? And that's massive. But then if you do that badly, you will just not be able to train it. It's just not going to take a step. It's going to take forever to take a step. And then the aspect here at the bottom is saying GP3 can be fine-tuned on a single node. That's because if you have GPU only, you can only do 20 billion. If you combine CPU plus GPU, you can get to 70 billion. If you combine all of the memory space, you can do actually a trillion parameter. Now, getting it right is the main sort of aspect or winning point for DeepSpeed, that we do it efficiently. But still, in theory, you can support it. Like, I think if you remember the OCDNN work we did a while ago with unified memory, the intent there was also similar, that we wanted to leverage all the memory space in the box available to train the largest possible model.
So I think OCDNN, you only had the blue and the orange.
Yeah, not the green, yes. So can we sort of extend an existing parallel training technology? So remember the first matrix that I presented on my second slide, right? So data parallelism, tensor slicing, pipeline parallelism. Problems with them. If you do replication, you cause memory explosion. That's where the word zero comes from. tensor slicing, you cannot scale beyond a single node. Pipeline parallelism requires significant code refactoring. So what does 0 give you? So 0 gives you all of them combined, efficiently scale across nodes, and no model code refactoring necessary. But how? I think we talked a lot about what 0 gives you, but how it gives you, right? So now think about memory efficient form of data parallelism. 0 is exactly that. In your standard data parallel training, these are your models. So layer 0, 1, 2, layer 0, 1, 2, layer 0, 1, 2, replicated everywhere, right? And so these are model states that every GPU has to retain. But in 0, we said, well, that doesn't make any sense. Why do I need to replicate them? I can say layer 0, layer 1, layer 2. And as a naive person, the first time I looked at it, it's like, well, this is kind of like model parallelism. Like this is layer parallelism, right? Like layer 0, layer 1, layer 2. But it's not. It's still data parallelism. So from a model training perspective of how you take steps, we're still data parallelism. This is done under the hood without actual model code changes needed. And we don't even communicate in a way that tensor, like a layer parallelism would do. And I'll talk about why and how. Similarly, if you want to extend it even further, you would do 0 with CPU or NVMe offload. So store in NVMe instead of your GPU, send from the CPU NVMe to GPU, and then broadcast or reduce as the 0 states. So here's a picture again with that same thing. Like look at the previous picture, it was all in GPU, right? Now we're all in NVMe. So layer 0, layer 1, layer 2. And what connects them? So PCIe connects them, right? And what is the bandwidth of PCIe? I think that's a question for the MAppage team. You guys should know. But the problem is it's limited. And so based on the theoretical or back of the envelope calculation, we require a 25 to 60 gigabytes per second bandwidth between these two. But the peak bandwidth on DDX2 is just 28 gigabytes per second. So that's a problem. So if you try to do this, this is just not going to work because it's 12 gigabytes per second. So what do you do then? Well, you reframe the problem a little bit, right? That's the sort of magic. That's why I was saying, like, instead of designing collectives, you redesign your application in a way that uses things more efficiently. So here we switch the problem and we say, okay, well, everyone can keep layer 0, 1, 2, but only parts of it that are needed for my personal training to proceed. And so what you do is you partition each of the parameter across GPUs, and then you send from NVMe to GPU in parallel. And what it allows you is to now use the collective PCIe bandwidth across all the GPUs. And then you use all gather and reduce scatter to construct and deconstruct. So now bandwidth is going to increase linearly with your devices. So now instead of 28 gigabytes per second, you can actually use 1.8 terabytes, which is more than enough for any kind of model movement. So that's why we're able to do that. And there is a really nice sort of video that's going to give you that entire story of what happens. So it's forward, backward update. And then I'll just let you see it for a bit. It's just trying to show like NVMe data movement from CPU to GPU and how we do an all gather and then reconstruct things. And you're done. So you started from here.
So do you use any audio interface to transfer your like DDS and all this?
We explored that, but we didn't really need it because of the partitioned access in some sense, but that does give a boost. So for specific movement here, if you do GDS, it does give a boost. But we have this thing called async IO library or AIO library in DeepSpeed, which actually is implementing it. So there are quite a few designs that they explored. Tanji in our team is leading that effort.
So basically, instead of GDS, you had a staged CPU design.
Yeah.
And then just for the reduce scatter and all gather from the GPU, you use the InfiniBand network.
Yeah.
Stage it back to the async IO library from the CPU to
NVMe. Yes. So just the recap of all those things. That's how 0 provides you, excellent performance. Some of the results, just kind of giving you a repeat of that. 3D parallelism. So before 0 infinity got really like adopted, there was this technique called 3D parallelism that I mentioned, right? So data parallelism plus model parallelism plus tensor parallelism, right? And that was the state of the art to get to the larger models. And you can see here that 3D parallelism in terms of parameters, it cannot just go and support the size of the models that we can support with 0. The other aspect is that, for example, here, for larger models, you can't even run, but even for the models that you can run, you see the throughput here is pretty maintained. So one of the challenges, if you remember, Hari, in the OCDNN was, as soon as you ran out of memory and then you use unified memory, the speed or samples per second of that larger model were almost 5 to 10x slower than the model that fit. And so that's not acceptable in some sense. Like a real model scientist doesn't want to use that system. So this kind of whole partitioning in zero infinity allows you to actually still give the teraflops per GPU. If you can see, they remain constant as you're increasing the model size, which is like the fundamental thing you need. And finally, the perfect linear scaling, sort of super linear scaling phenomena I mentioned. So that concludes zero infinity. I know you have questions.
Like I recently released FSDP,
yeah,
which I think maps to
0.3. It's a re-implementation of 0.3.
Oh, yeah. So is there like an advantage using?
There is no advantage of using FSDP over DeepSpeed. Yeah.
Do you think PyTorch is catching up to DeepSpeed?
Yeah. So when we first proposed DeepSpeed, there was a project to upstream. There was a collaborative effort to upstream DeepSpeed into PyTorch. And that's where FSDP started. So FSDP, the name, and 0.1.2, they still call 0.1.2 for the stage 1 and 2, but then the third one, they call it PyTorch FSDP. But FSDP is a re-implementation of 0.3 by the PyTorch team. And so there are many reasons for that. Let's not go into it, but it's essentially the same thing. So it shards pretty much all the parameters across, and there is even the initialization, everything is the same as DeepSpeed. So if you have a code that works with DeepSpeed, probably changing it to FSDP is not going to give you anything. But there are people who are just starting, so like maybe they're just living in the PyTorch ecosystem. There it would make sense to replace DDP with FSDP. I have a detailed blog post comparing these technologies with scaling as well. So feel free to take a look at that. I'll also point it out.
Parts of Microsoft seem to be being delivered in CXL-based memory fusion. For example, it's like Optimus paper, home. It basically covers, I think, the output like future, whatever. But then you also could you leverage the CXL-based memory also actually potentially offer much higher?
Yes. Yeah, there is that, and there is also this startup called Infabrica, and there are many teams which are talking about next generation of hardware. So we do work in collaboration with them a little bit to learn how we can extend DeepSpeed to use their APIs to take advantage. So there is that, yes, nothing concrete, but still upcoming.
Yeah, so how does your throughput get impacted when you compared to the HBM memory that you use? So suppose that you could fit all of your parameters in multiple GPUs. You had like millions of parameters to train, and you wanted to compare the throughput of the training as opposed to having trillions of parameters that utilize the NVMe.
Yeah.
Do you see that it will be expected to be a huge difference in the throughput?
So that's what we aim for, to not have any difference, right? So the whole optimization is around, okay, here is my teraflops per GPU. For V100, it was around 50 teraflops per GPU. For A100, it's around 150, right? And so we want to see, okay, nothing below 150 teraflops per GPU is acceptable if you're training real models, right? And so how do you get there, even when you're using NVMe and GPU and everything? So the whole optimization or research work kind of is focused to not see degradation. There is still, like, there's no magic, right? But the degradation is we try to minimize that degradation so that you can still train with reasonable speed. Because now the model is also much, much bigger. But there is, I have my Azure blog. If you search for Azure plus DeepSpeed on Google or Bing or whatever, you'll be able to see it. The first hit, it's just scaling DeepSpeed with the 175 billion model all the way to 2 trillion model. Same teraflops per GPU. Zero difference. Yeah. Okay, so I don't think we have time to cover this. Sure. So this is fairly exciting and also really cutting edge, work. A mixture of experts is a special style of transformer models, which are gated, and they are sparse. It's not very new, but people know them now because of all the ChatGPT and GPT-4. It's actually a 2017 paper by Noam Shazir, and this was called Outrageously Large Neural Networks, the Sparsely Gated Mixture of Expert Layer. Then G-Shard paper came with a 600 billion parameter MOE model, and then the switch transformer paper came with a 1.1 trillion MOE model. Now, keep in mind that 1.1 trillion MOE model is not equal to a 1.1 trillion dense model. Their just capability is not there. Think of a 5x relationship. But in a nutshell, how it's different is because now, so this is your standard transformer. I'll use the pointer so I can explain. This is your transformer block. The transformer block is fairly simple. You have a multi-head attention, you have a feed forward and things around it, right? You take these blocks and add multiple of them to make a transformer, which is these. Here it's showing like, okay, this is my MOE transformer encoder. A standard dense model looks like this. It does have a feed forward component, but if you want to change it from this feed forward to here, this has MOE. And this block is called the MOE block or the MOE layer. And you see this green thing here talks about gating, which means that each token that you're feeding to the model is going to go only to one FFN or one expert. That's why it's called mixture of experts. So think of a feed forward network, or some people call it MLP, like multi-layer perceptron. These are basically experts, and each token goes to each expert based on a gating function, and the gating function is learnable. So we learn the gating function during the training. But it's more interesting when you actually do multi-GPU MOE. That's what we call expert parallelism. And so now you need this all-to-all to happen because you have tokens starting from here. That token can actually go here all the way. So you need this all-to-all to move the tokens from here to there and then come back and get that completion. So there are two all-to-alls in the forward. There are two all-to-alls in the backward. And so from a communication perspective, they're very interesting models to explore. You have a lot of, like, now you have like interesting application to change your MPI library or work on it to find on optimizations. Switch transformer is just a little bit of an improvement, so we'll skip that part. And so essentially, dense models, MOE models, what you get is you have a larger model, but you have the same compute requirement. Whereas in dense model, the larger the model, the higher the flops you need to do. So that's not scalable. This is fairly scalable, but how do you scale it and still get quality? That's the whole sort of notion. Like, you can keep increasing the model, but if you do too many experts, then the gating function will be so wide, it's not going to give you the same accuracy as a dense model. So there's a lot of interesting model and system research, but essentially the expert parallelism is the most interesting systems perspective for people like, sitting in this room. And so here is all the focus that we had: redesign Nickel to do certain things, make an all-to-all faster. If you inference on these models, you will need latency sensitive all-to-all, which is nowhere to be found. But in HPC community, it has been known widely. So it makes sense to mix and match certain parts because all-to-all is there, but all reduce and the standard other collectives are still being used in the model. So data parallelism still exists here. It's just expert parallelism is a certain part of the model. But at least in our team, we believe that next generation of AI scale, if you want to achieve on current generation of hardware, the only way to go about it is the MOE models. And so from a training perspective, they're a promising path, but is it practical to do? And there were a lot of challenges that we were trying to resolve at the time. It was limited in scope. No one had known how can you use a ChatGPT style or GPT style model. It was mostly like BERT model or encoder decoder translation model that we're using MOE. So that was the initial work. Then switch transformer changed it. There's massive memory requirements. So if it's 10x larger to a quality equivalent dense model, how are you going to do inference? Massive model size, it's going to be slow. So we explored quite a bit. My first line of work, major work that got published as a blog post with the Microsoft research was DeepSpeed MOE training. We created a training system, created an API. Then we extended it with the MOE inference, because now we were able to train models with MOE models with DeepSpeed. But how do you do inference? And so there are these 4 aspects of what we covered. And you can see all aspects, DeepSpeed offered really good throughput over state-of-the-art PyTorch. When I say baseline here usually means like off-the-shelf PyTorch. And so DeepSpeed builds on top of PyTorch and then extends it. So giving you these massive speedups to make things happen. And so just for a reference point, right? So a 1 trillion MOE model inference, you can do under 25 milliseconds. If you have a dense model like GPT, which is about 200 billion, it will take about 50 milliseconds to inference. This is not acceptable. This is acceptable because human, you don't want to wait that long for your first, token to get generated. So there is a threshold. Again, another chart of parallelisms combined. So flexible multi-dimensional parallelism is supported. Now you have another dimension. So The first chart was all about data, model, and stuff, right? But now you have experts and expert parallelism combinations with each of those. Far more complicated and involved. We still sometimes get confused when you're working with this system. But the API is fairly simple. You just extend your model by an MOE. That MOE comes from DeepSpeed. You import it from the DeepSpeed.moe layer and allows you to train. Like you have a standard BERT model, you just add there. You can experiment with it. So it's a quick experiment in terms of models. It's a fairly long experiment if you do it at scale. There are some performance numbers, as we just all love performance. So DeepSpeed, kind of like when we first publish it, we could train 8x bigger models, or you could think about 8x fewer resources for the same model size. That was the intent behind the DeepSpeed MOE system. Again, near perfect sort of linear scaling, beyond that actually for some cases. And finally, the model that we trained was much cheaper to train, which is an interesting phenomenon that very few people in the world would probably understand. So I want to spend a minute on this. So you see here, there's a 1.3 billion dense model. This is a loss curve, lower is better. And you train a 1.3 billion dense model, you never reach this. You know that this model is just not going to be capable. You can train it 100 times, it's not going to come down. The model doesn't have the capacity to learn anymore. Then you train a 6.7 billion dense model, which is this yellow line, and you're going to see, wow, this dense model is super awesome. It's so much better, 2.45 and 2.15 worlds apart. And 300 billion here means that this many tokens have been seen by the model. So we said, well, okay, can we extend the 1.3 billion dense model and add experts to it? And so we added experts progressively. So we said 8 experts, 16 experts, 32 experts, 64, and 128. And then we just stopped at 128 because beyond that, there was diminishing returns. And you can see that 1.3 billion plus 128 experts actually beats the 6.7 billion dense model. So the equation is about 5 to 8x larger, but 5x cheaper to train. So 6.7 billion dense model is going to take, I think, 50 samples per second or something, whereas this blue line is going to give you almost 300 samples per second. So it's 5x faster to train an MOE model, which is even 8x larger than the dense equivalent. So there is a lot of value in training MOE models.
What's the expression?
This is going to come next. So that's the immediate question everyone's like, oh, we have 8x more parameters. It's going to be dead slow to inference. Who wants to use MOE? And that's the kind of thing that we explored. And interesting, there is some very unique properties of MOE inference that allow you to actually infer these models on multi-GPU much faster. For dense, the best case is you'll go linear. Especially for throughput, you can do super linear speedups because now you don't have a dependency. You can break the dependency and you can do multiple experts per GPU independently. So you can do data parallelism, no communication needed at all. Similarly, we have this low latency along with super linear throughput. So that's a phenomenon, but I'm going to talk about the concern, right? So if you use PyTorch MOE, you're going to see massive, because it's 8x larger, is going to give 8x lower latency, right? Because PyTorch doesn't know it's an MOE model. But DeepSpeed is aware of an MOE presence and it deals with it in a specific way, and you can scale across nodes. So this is on 128 or 256 GPUs. And you can see that latency is almost 7 to 8 times faster than the state of the art, which brings it to a point where that number we retain, right? So 25 milliseconds, that's the sort of the upper boundary. Beyond that, it's not acceptable in the inference world. There is also many other interesting things in this slide, but just trying to give you an idea how we make MOE inference practical with DeepSpeed. So if you were to take this graph and you say, oh, PyTorch dense model is here and MOE model is 2 to 3x slower, I'm not going to use MOE. Yeah, it trains faster, but it doesn't infer faster. So that's what we're trying to achieve. And we're trying to bring the MOE speed of inference much faster than the dense model inference. And these are not same size, they're quality equivalent, which means the same 6.7 billion quality equivalent and the 52 billion MOE. There's a lot of details I'm skipping. This is actually a ICLR paper, I think, if we talk about how we do the quality equivalence and stuff. So I think the key message here is MOE models are interesting. They're going to enable the next generation of AI scale on current hardware. Unless we do groundbreaking new hardware, we're fairly limited on these model scales and optimizations. So with that, I'll conclude. There's a lot of software aspects. You people are experts in using C++, should be no problem using this in Python. But there is a broad sort of like framework. We have higher level APIs, lower level APIs, and things like how we deal with the lower level libraries is through DeepSpeed ops. It's a fairly JIT build system. So even like you can write an op in 20 minutes and compile it in 5 minutes. And we can say, oh, you have a new op in DeepSpeed, if you know what you're doing. Yeah, so it's a fairly easy to plug into system. Runs pretty much everywhere. This I already showed you. To change from a normal PyTorch model to a DeepSpeed model is massive 4-line code that you need to use. And then you're pretty much done. Okay, I think we will conclude, and I'm just going to show you or flash all of these anyways. There is also an interesting repository we call DeepSpeed examples, where all the client examples are pretty runnable. So you can clone DeepSpeed, you can clone DeepSpeed examples, run it, and trigger all these interesting things. Even for MOE models, we have scripts now. And for inference, we typically try to extend Hugging Face models and make them faster. So this is a standard Hugging Face model. Like someone was asking, how do I use Hugging Face model, right? So literally these 5 lines of code, you write it on your current Python shell, you're going to get a model called GPT-New 2.7b, and you say DeepSpeed is blah or MVAPITCH is blah, and then it's going to generate 50 tokens, predict the next 50 tokens for you. If you do that without this block, it's going to take like, I don't know, 15, 20 milliseconds. If you take it with DeepSpeed, it's going to take like 2 milliseconds. So that's the accelerated part here. And we welcome contributions. So make your first pull request, and we'll be happy to review it. Thank you.
Any other quick questions?
May I ask some question online?
Yes.
Oh, sure.
Go ahead.
Okay. Hi, this is Yuxiong here. Very interesting talk, and I'm really impressed by the MOE results. I think people have, of course, have a lot of interest in MOE, but there are also a lot of concerns. Part of which is due to people don't quite understand the landscape around MOE, and it's very quickly changing. I think one common perception is that the current hardware, especially GPUs, are not that suitable or like optimal for MOE models. And GPUs are slightly better, but still not ideal. So could you comment on that? And then relatedly, do you think with the current hardware and with like optimization provided by DeepSpeed, we are ready to train like maybe GPT-3 or GPT-4 scale MOE models from scratch?
Absolutely, you're ready to do that. So that was the initial skepticism. So any project that we do right at Microsoft, there is also our leadership is like, why are we doing this? And so I want to always show this graph to everyone who says MOE models cannot be good. This is a 1.5 trillion MOE model, and which is massive compared to today's scale. So it's like a 530 billion quality equivalent, right? Or sorry, 175 billion quality equivalent. And you can see that it's 4.5x faster to train, 9x cheaper when it comes to inference throughput. So DeepSpeed system today, like public DeepSpeed system today, is ready to go if you want to train your next generation of MOE model along with its inference stack. So there's absolutely no skepticism needed there. I agree with the perception is there because of this. So like the red arrow here is the perception. And that's not just a perception, it's actually measured results. So if you have a dense model, you run an MOE model and you're like, okay, this whole MOE line is not acceptable because we cannot deploy this in production. But that's what we are changing with DeepSpeed, and we're able to do it fairly significantly. So yeah, you're ready to go, and feel free to like create an issue or like send an email to us and we can get you started.
Great, thanks. Yeah, we're very much looking forward to trying it out.
Sure, awesome.
Yeah, on the topic of MOE, there was this recent publication at ICICLE MOE. I'm not sure if you're aware of it, but they basically like do pipeline parallelism for MOE.
Yeah.
And they also show very good speed.
Yeah.
So I'm like wondering with DeepSpeed and like, is it purely optimized in the all-to-all, or are there any?
Yeah, it's not just the all-to-all. It's for inference. There's a lot more than that. That's all in the paper, the SC paper, and also the ICLR paper. I'll point you to the papers. But essentially, difference between pipeline-based MOE and DeepSpeed MOE is that DeepSpeed MOE is rooted in expert parallelism. So we don't do a lot of like combinations of parallelism because we essentially don't like model rewrite. Our combination is with 0. So MOE plus 0 family works together. So then you pretty much have an infinite scale. Like if you can train a 1.5 trillion MOE model, you don't necessarily need pipeline parallelism. And so that was our intuition when we were building the system. So when I first built it, it was just MOE. Then we said with expert parallelism. And so it had limited scale. And then we combined it with 0 stage 1 and 0 stage 2. And now you have pretty much endless base model size as well as the expert size. So it's a comparative system, I would say. I have not explored the system, so I cannot comment on performance, but conceptually, these are the two different lines. Does that make sense?
So I have like two questions. The first is more like general one. So when we talk about large language models or like foundation models, as they like become bigger and bigger in the parameters, like the training is like always considered it can be done, for example, in house by companies, they can do a lot of fancy tricks, right, accelerate it. But like for inference, like which trend do you consider is like the future? Like do people like send requests to the servers in the company and the company do the inference and then send back the results, or like people can do them on their own laptops? Because like currently for those, if we say like ChatGPT, that like these models still cannot fit in the personal computer, still has to be, processed on.
There are two challenges there. One is the availability of the model itself. So ChatGPT, you cannot download. Even if you could have a 200 gigabyte GPU on your desktop, it's just OpenAI is not going to give you the model, right? It's through an API. So all those inferences are happening in Azure servers, of course. And you don't have any control over it. But when you sort of say that I have an open source model, let's say Llama or MPT or Falcon or whatever, you download that model, and depends on the size of the model. If it fits your CPU, you can do an inference. But let's say now that you've figured out that I can actually get something useful out of this model, you would still want to deploy it in web servers, right? And web servers which are based on GPUs or whatnot to replicate, increase the throughput, because you will have multiple millions of requests coming to it. So that entire space is fairly company dependent. Like if it's a startup, there's going to either use an Azure solution, or like Hugging Face has these accelerated inference endpoints. And so you can deploy your custom trained models through those Azure endpoints or Hugging Face endpoints or any of the infrastructure, or you can build your own infrastructure. There's a lot of like, I think it's just the beginning, right? So everyone is exploring new solutions. So there's no blockage. The only blockage is, let's say if the model is 175 billion, you can't fit it. Can you do something about it? And there are techniques, like there is QLoRa and there is LoRa and there is quantization, and you convert the model from, like we went from FP32 to FP16, now to FP8 and int8 and int4 and int2. And so we're trying to reduce the model as much as we can to fit them on the GPU memory and then do some inference. There's obviously a little bit of quality loss in these things, but we do a bunch of work there too. Yeah, we have a whole, I did not present that. There's a whole compression line for inference of the models, like zero quant, and my colleague Joey, he's from Berkeley. He joined us two years ago, and he works fairly specifically on that problem to fit larger and larger models.
I think following that question is like, you talk about like composition techniques, but like there is very critical feature about the models is like, if you know, like the autoregressive property of this model. So basically you can accelerate like virtual generation.
Yeah.
You can do a lot of techniques, but because it's, more dependency, you cannot break up that dependency between your tokens. So you have to do the forward.
Yeah.
But that is like a very strict dependency there. You cannot simply break that up.
There are some clever ways to do it, or at least there are clever ways to parallelize it, because tokens are not unique, right? So even from a multi-query perspective, millions of people are doing the same queries essentially, right? So there is techniques, but I'm not going to go into the details of them. There are fairly model-specific techniques to optimize that. Inference optimization is the next big thing. There's a ton of things from models perspective, systems perspective, and also a convergence of models and systems perspective. So yeah, it's a fairly big subject.
I will do that offline.
Offline is fine, yeah.
So let's then close the thing. So let's again give a lot of thanks to open application. This is familiar to you, yes. Right? It is the mug, which we do the MRP user group meeting. Of course, you have been involved in that. And of course, the T-shirt, the SC T-shirt. So these are some work for you. Okay.
Thank you, Dr. Panda. Thank you, everyone, for listening. It was fun having this talk here.
Yeah, so we'll conclude the session. Thanks a lot.
From here or where? 263. Yeah. 263. Yeah.
Where are you going with that?